How do SIGSEGV signals cause C++ segmentation faults? Imagine your program trying to peek into a part of memory it shouldn't access. That action triggers a SIGSEGV signal, which is like the operating system's way of saying, "Hey, something's wrong here." In C++, this signal is what causes a segmentation fault to happen. A SIGSEGV, or segmentation violation, is sent by the operating system when a program tries to access memory that it doesn't have permission to use. Think of memory as a set of labeled boxes. If your program tries to open a box it isn't allowed to, the OS steps in and sends that signal. This prevents the program from messing up other parts of memory or causing unpredictable behavior. In C++, this usually happens when you try to read or write outside the boundaries of an array. For example, if you have an array of 10 elements and try to access the 15th element, you're stepping into an allocated territory. The OS detects this illegal access and sends the SIGSEGV signal. Another common cause is dereferencing a null pointer. If your pointer hasn't been assigned a valid memory address and you try to use it to access data, the OS sees that you're trying to reach into memory that doesn't exist. It then sends the SIGSEGV signal. Modifying read-only memory, like string literal, can also trigger this signal. String literal are stored in protected memory areas, so any attempt to change them causes a violation. Similarly, if your program frees memory and then tries to access it afterward, it leads to a useAfter-free error, which the OS catches with a SIGSEGV. The hardware enforces memory protection by dividing memory into segments with specific permissions. When your program violates these permissions, the hardware triggers a fault. The operating system then translates that fault into a SIGSEGV signal and terminates your program to keep everything stable. Debugging these faults is about understanding where your program is trying to access invalid memory. Using tools like the new debugger, you can see exactly which line caused the problem. Checking pointers for null or uninitialized values before using them helps prevent these errors. Also, always validate array indices and buffer sizes to avoid out-of-bounds access. Managing dynamic memory carefully is key. Make sure to allocate memory properly and free it only once. If you do this, your program is less likely to cause a segmentation fault. Using sanitizers like Address Sanitizer can also catch invalid memory operations during development. By understanding how SIGSEGV signals lead to segmentation faults, you can better trace and fix memory access issues in your C++ programs. This knowledge helps you write safer, more reliable code that avoids these common pitfalls.